every single time you open an app on your phone, whether you are swiping on a dating profile, buying concert tickets, or, just streaming a movie, there is this hidden, high-stakes, philosophical battle going on right behind the glass of your screen.
Yeah, it really is a battle.
Right. Because when a company builds that software, they are forced to make a fundamental choice right out of the gate. Do they put all their eggs in one massive, incredibly sturdy basket, or do they try to manage this chaotic, invisible web of a million tiny, independent moving parts?
And that choice dictates everything.
Exactly. So welcome to this deep dive. Today we are pulling from a massive stack of research, specifically focusing on some incredible excerpts from a comprehensive guide on software architecture patterns, Volume 4, covering episodes 16 through 20.
It's a lot of dense material for sure.
It is. But our mission here is to demystify exactly how the digital tools you rely on every single day are actually built. We're looking at how they scale to handle millions of users at once and, well, how they are kept running without collapsing under their own weight.
Which happens more often than you'd think.
Oh, yeah. So we are going to translate these incredibly dense engineering concepts into a story about human organization and ultimately a literal fight against the laws of physics. So, okay, let's unpack this. Software architecture isn't just about writing code. It's a high-stakes philosophical choice. And the absolute baseline of all of this, the starting point for almost everything, is a concept called the monolith.
Right, and the monolith is, it's a very literal term. It is just a single code base. It is deployed as one single unit, and it runs in one single process on a server.
Okay.
So if you think about an e-commerce website, all the user interface logic, all the business rules for calculating shipping, the database access for inventory, all of that just lives inside this one giant unified program.
So it's all glued together.
Exactly. Which means if the developers need to deploy an update, they have to deploy the entire massive thing. If they need to handle more traffic because of a holiday sale, they just run more copies of that entire monolithic application across different servers.
And the fascinating thing to realize from the sources is that monoliths actually have this incredibly unfair, bad reputation in the tech world.
Oh, completely.
Like, people talk about them like they were these dusty, old-fashioned relics that you should avoid. But a well-built monolith is actually cheaper to operate, much faster to deploy early on, and way simpler to debug than modern alternatives.
It really is a phenomenal starting point because of that sheer simplicity.
Yeah, and we are not just talking about small mom-and-pop websites either. Massive, world-class successes were built exactly this way, like Stack Overflow, Basecamp, and even Shopify in its early years. They all started as giant monoliths.
Because in the early days of any product, a company's primary goal is just finding out if people actually want the thing they are building, They need to move fast.
Right, no time to overcomplicate things.
Exactly. With a monolith, you don't have to worry about complex network communications. If your checkout system needs to verify a user's address, it literally just looks at a different sector of the exact same system's memory.
Just a quick internal check.
Yeah, it happens in microseconds. It is instantaneous and mathematically guaranteed to work, but the friction starts to emerge when a company hits massive scale.
Yeah.
As that single code base grows into millions of lines of code, it becomes harder for anyone to mentally map out how it all works. You end up with hundreds of developers essentially stepping on each other's toes, trying to modify the same interconnected files.
So to fix that developer traffic jam, companies basically do the exact opposite. They take that giant monolith and they shatter it into pieces.
Oh, yeah.
Which is the shift to microservices.
Right.
You break the app into isolated, independent services. Like, one piece just handles user logins, one piece just processes orders, one piece calculates taxes.
Yep, completely separate.
Each tiny piece has its own code base, its own separate database, its own dedicated engineering team, and they just talk to each other over the internet. But wait, I have to push back on the conventional wisdom here.
Go for it.
Isn't a monolith essentially like a giant Swiss Army knife? If the little pair of scissors breaks, you have to take the entire knife into the shop or just throw it away. Microservices sounds so much safer and more logical. If the tax calculator breaks, you just swap out the tax calculator. The rest of the site stays up. So why do the sources flash such a massive warning over microservices, claiming they are the biggest source of modern software failures?
Well, what's fascinating here is that when you break apart that Swiss Army knife, you don't just get clean, independent tools. You suddenly inherit the absolute nightmare that is a distributed system.
A distributed system.
Right. Remember how we said a monolith checks an address by just glancing at its own memory? In a microservices architecture, that check now has to be bundled up into a digital message and fired across a physical network cable to a completely different server.
Oh, wow.
And networks are hostile environments. They fail, cables get cut, routers drop packets of data. Suddenly, a really simple user action like you clicking Add to Cart might require 10 different independent services to successfully talk to each other over the network in a fraction of a second.
Wait, if a single click spans 10 different services and just one of them drops the ball and fails,
Yeah.
how do you even know which one broke? You'd need some kind of X-ray vision for your network just to find the missing data.
You're hitting on exactly why this destroys so many engineering teams. You have to implement incredibly complex tracing systems where a unique ID is attached to your specific mouse click.
Just to track a click.
Yes, and that ID is logged at every single hop across the network just so developers can hunt down where it died. And the sources point out a massive cautionary tale from the late 2010s about this.
Oh, the distributed monolith thing.
Exactly.
Right.
Microservices became the hot new trend. Everyone wanted to use them, so companies adopted them by default without understanding the brutal operational costs. What resulted was a wave of distributed monoliths. Companies shattered their code bases, but they didn't separate the logic properly. So the order service still strictly required the inventory service to be awake and responding in order to function.
So they're basically still tied together.
Completely tied together. They couldn't actually deploy anything independently without breaking the whole chain. They took on all the massive latency and network failures of microservices, but kept all the rigid lock-in of a monolith.
Wow, worst of both worlds.
Exactly. The golden rule in software design is to start with a cleanly organized monolith and only pull out a specific microservice when the pain of keeping it together is literally worse than the pain of managing a distributed network.
So breaking a monolith apart to scale solves one problem but creates a massive new one, which is how did these separate pieces effectively talk to each other? And the wild part of this history is that the tech industry actually tried to solve this exact communication nightmare way back in the late 1990s and 2000s.
Yeah, long before the word microservices even existed.
All right, we have to rewind the clock to service-oriented architecture, or SOA.
Yes. SOA dominated the enterprise software world for a decade. The core goal was enterprise-wide reusability. Before SOA, massive corporations had completely isolated redundant systems.
Like silos?
Exactly. The billing department built their own database to look up a customer. The shipping department built a totally different one. The marketing team had a third. SOA came in with a mandate, let's build one universal customer service.
Okay, makes sense in theory.
Right. Then the website, the mobile app, and the warehouse system will all just send requests to that one shared service.
But the way they connected everything was through this massive piece of central infrastructure called the Enterprise Service Bus, or ESB. These were like heavy centralized hubs sold by IBM, Oracle, TIBCO.
Very expensive, very heavy.
So if I'm understanding this, they built this massive central bus to route all the messages, translate data formats, and direct traffic between every department. Isn't that just replacing a giant application bottleneck with a giant communication bottleneck? Like building a 10-lane highway that forces all traffic through a single, slow toll booth.
Yeah, that's a great analogy, but it's actually worse than just a slow toll booth. Imagine if that toll booth operator also had to stop you, check your cargo, translate your license plate into 5 different languages, and then give you directions before lifting the gate.
Dear God.
The ESB wasn't just routing traffic, it was heavily transforming the data. Because older systems relied on rigid, heavy instruction manuals for communication, every single message had to be wrapped in layers of strict formatting just to be understood.
So it was just incredibly slow.
Very slow. And it created a massive organizational bottleneck. If a developer wanted to change how the order system talked to the billing system, they couldn't just write the code. They had to submit a ticket to the central ESB management team and wait weeks for them to update the master routing rules.
So the tool designed to make the company move faster became the exact reason they couldn't get anything done.
Precisely. SOA was very top-down. It was entirely focused on central governance. Modern microservices actually took the core idea of SOA reusable independent services, but flipped the execution to be bottom-up.
Ah, decentralized.
Yes. Instead of a heavy central toll booth, modern microservices use lightweight direct network calls. But it's vital to note that SOA is not entirely dead. If you look at massive legacy banking systems, telecom companies, or government infrastructure today, you will still find those heavy central routing buses running the show.
Right, but even with those lightweight direct pings in modern setups, they still run into a huge traffic problem. If your order service directly pings the payment service, and the payment service is running slow because it's, say, Black Friday, your order service is just sitting there completely frozen, waiting for a response.
Which cascades and crashes the whole system.
Exactly. So to avoid that single toll booth bottleneck, they had to stop waiting in line entirely.
They had to abandon request-response communication. Request response is what we've been talking about so far. Service A asks a question, Service B calculates an answer, and Service A pauses everything it's doing until it gets that answer back.
Which brings us to the event-driven shift.
Yes. The evolution beyond this bottleneck is event-driven architecture.
And here's where it gets really interesting. Think about the mechanics of this. Request response is basically like calling a friend on the phone to say you got a new job. You dial the number, wait for them to pick up, tell them the news, and you physically have to stay on the line, doing nothing else, waiting for them to say congrats.
Right, you're blocked.
But event-driven is like posting that new job on social media. You just broadcast it. You say, hey, an order was just placed, and that's it. You instantly go back to work. Then the email system, the analytics, and the warehouse system, they just like or react to it on their own time, at their own pace, without keeping you on the phone.
If we connect this to the bigger picture, the mechanism powering that social media timeline is a piece of infrastructure called a message broker, technologies like Apache Kafka or RabbitMQ.
Okay.
The beauty here is total decoupling. The service that produces the order-placed event has no idea who is listening to it. The broker simply organizes the events into streams.
So you can just plug new things in.
Exactly. If you add a brand new fraud detection system tomorrow, you don't touch a single line of code in the checkout system. You just connect the new fraud system to the broker and tell it to subscribe to the order-placed stream.
And it creates this incredible resilience for the listener using the app.
Yeah.
If the warehouse shipping system completely crashes, your checkout screen doesn't freeze. The order system just keeps taking your money and posting events to the broker.
And the broker just holds on to them. When the warehouse system finally reboots hours later, it just reads the backlog of events and catches up. It handles sudden bursts of traffic gracefully.
But it's not all sunshine and rainbows, right?
No. The brutal costs of building this way are massive. Debugging becomes 10 times harder. When a single user click triggers a massive invisible cascade of asynchronous reactions, and one of them fails silently, finding the error is a nightmare.
And there's that other issue, right? The exactly once delivery problem.
Yes, the infamous difficulty of exactly once delivery. How do you guarantee a message broker delivers an event exactly one time, never dropping it in a crash, and never duplicating it during a retry?
How you?
You basically can't. It is mathematically almost impossible to guarantee exactly once delivery efficiently in a distributed network. Most architectures settle for at least once delivery.
So it might get sent twice.
Right. In the event of a network blip, it might accidentally deliver the ship this order message twice. This forces your engineers to build what's called idempotency into every single consuming service.
Idempotency.
Mm-hmm.
Meaning the receiving system has to be smart enough to say, wait, I already shipped order number 1, 2, 3, 4, 5. I'm ignoring this duplicate.
Exactly. The complexity shifts from the communication pipe directly to the services themselves. This also birthed advanced patterns like CQRS and event sourcing, which completely separate how you read data from how you write it.
Okay, so picture the state of things at this point. We have shattered our monoliths into dozens of independent microservices. We have them firing thousands of asynchronous events at each other through message brokers.
It's a lot of moving parts.
A ton. And the operational nightmare of just keeping all those physical servers patched, updated, and running is immense. What if you could just surrender that burden entirely?
Which brings us to a very provocative buzzword, serverless.
Right. And it's a bit of an illusion, isn't it?
It is highly misleading. The server still exists. There's still a physical silicon chip in a massive data center somewhere. But from the developer's perspective, the management of that server has vanished.
So they just don't deal with it.
Exactly. You don't lease it. You don't install an OS. You don't monitor CPU usage. You just write a small piece of code, upload it, and the cloud provider executes it on demand.
Like function as a service, popularized by AWS Lambda back in 2014.
Yep. Theasis. If no one uses the feature, the code sits dormant, it scales to 0, and you pay $0. But if 1 million people hit it at once, It instantly scales to 1,000 instances, and you only pay by the millisecond of execution.
But I have to challenge the perfection of this model.
Right.
I mean, I love the marketing coup of the word serverless. It's like renting a hotel room, you get the bed, but you don't have to fix the plumbing.
Right.
But if I don't own the plumbing, aren't I totally stuck if the hotel decides to change the locks? The vendor lock-in sounds terrifying.
Oh, I totally agree. It's a massive trade-off. Vendor lock-in is huge. You are weaving your application deeply into that specific cloud provider's proprietary ecosystem.
You can't just easily move to another cloud.
No, it's an agonizing rewrite. Plus, serverless functions are stateless by design. They wake up, do one task, forget everything, and die.
So not good for something like a live video game.
Exactly. And financially, for steady, high-volume traffic, serverless is actually more expensive than traditional dedicated servers.
Really?
Yeah, paying a premium for every single millisecond adds up fast if it's running 24/7. And we haven't even talked about the cold start problem.
Ah, right, because it's asleep.
Yes. When a function has been dormant, the cloud platform has to physically find an available machine, boot up the container, load your code, and initialize it. That cold start takes hundreds of milliseconds.
And speaking of milliseconds, even if your serverless function scales instantly and is fully awake, it still has to physically travel to the user. And that brings us to an ultimate hard boundary that no amount of cloud computing can fake the speed of light.
It's the one bottleneck we can't engineer our way out of. Information cannot travel faster than light.
The sources gave a really stark example of this. A round-trip network request between a user's phone in Sydney, Australia, and a centralized cloud server in New York takes a minimum of 220 milliseconds.
Right, and that is a hard physical limit.
And 220 milliseconds might sound fast,
Yeah.
but for competitive gaming or real-time video or algorithmic trading, that lag makes the app feel completely broken. So what does this all mean? We spent the last decade tearing our monoliths apart, moving all our code into these massive, centralized cloud data centers.
Yeah.
And now edge computing is pushing it all back out to local cell towers and internet providers just to shave off a few milliseconds.
Are we just moving in circles?
It definitely looks like that, but it's not a circle, it's an evolution. We aren't abandoning the cloud, we are extending it. Edge computing via companies like Cloudflare, AWS, Vercel pushes those serverless functions to hundreds of local micro data centers worldwide.
So closer to the actual users.
Exactly. So when that user in Sydney clicks a button, the request is processed by an edge server sitting right there in Sydney, returning a response in 10 milliseconds instead of 220.
Which is vital for caching and dynamic rendering. Yes, and filtering IoT data locally. Think of a smart city with thousands of cameras. You can't send all that raw video back to Virginia. You process it locally at the edge and only send the text alerts to the cloud.
But the edge has to have limits, right?
Oh, severe limits. Edge nodes have way less raw power. And the absolute hardest problem is keeping data consistent across hundreds of nodes globally. It's incredibly difficult.
Wow. It really puts everything into perspective. Whether you are swiping on a dating app, buying concert tickets, or streaming a movie, the speed and reliability you experience is the direct result of these invisible architectural choices.
Balancing monoliths, microservices, brokers, and edge nodes.
Exactly. And the sources leave us with a final mind-bending thought to mull over. The boundary between client, edge, and cloud is rapidly blurring.
It really is. As edge computing puts more processing power directly in our neighborhoods or even local cell towers, imagine a future where the concept of a remote backend server practically vanishes.
Yeah. What happens when the edge becomes the literal smart devices in our pockets, talking directly to each other and filtering data ambiently, just bypassing the cloud entirely?
It's going to change everything all over again.
It really is. Well, thank you for joining us on this deep dive. Keep exploring the invisible structures that power your digital world.